Right now, your phone recognises your face in a fraction of a second. Your car can see pedestrians. Your voice assistant understands your questions. These things feel normal. 10 years ago, they were impossible. On September the 30th, 2012, 3 researchers in Toronto did something that changed everything. They entered an image recognition competition and didn't just win, they obliterated the competition by a margin that shouldn't have been possible. First place with a 15.3% error rate. Second place had a 26.2% error rate. In computer vision research, improvements typically measure in fractions of a percent. A gap of 10.8 percentage points? Unheard of. This wasn't an improvement, this was a revolution. Alex Krzyzewski, Ilya Sutskever and Geoffrey Hinton, they had built an 8-layer deep convolutional neural network. They called it AlexNet. They trained it on 2 graphics processing units for 5 to 6 days. Within months, the entire computer vision community abandoned decades of traditional methods and converted to deep learning. The following 8 years would see AI transform from useful specialised tool to technology reshaping civilization. This is that story. AlexNet succeeded because 4 elements converged simultaneously. Let me show you what happened. First, big data. Think of learning to identify cars. If I show you 10 pictures, you might recognise, say, Toyotas and Fords. Show you 100, you'll start catching makes and models. But show you 1 million, you become an expert. ImageNet gave AI that million example education. 1.2 million labelled images across 1,000 categories. Previous datasets, thousands of images. This was like jumping from elementary school to a PhD programme. Second, GPU acceleration. Graphics processing units originally designed for rendering video games proved extraordinarily effective at the parallel computations required for neural network training. GPUs accelerated training by 10 to 50 times compared to traditional processors. What previously took weeks now took days. Third, architectural innovations. AlexNet introduced several technical innovations. ReLU activation functions, essentially a mathematical trick that stopped the network from getting confused when processing lots of layers. Think of it like noise-cancelling headphones for neural networks. Dropout, randomly deactivating neurons during training to prevent the network from just memorising the training data instead of understanding patterns. Data augmentation, artificially expanding the training dataset through transformations. One image becomes dozens of slightly different versions. Fourth, persistence. In 1986, Geoffrey Hinton published breakthrough work on neural networks. The AI community's response? Interesting, but it'll never scale. For 40 years he watched his ideas get dismissed, defunded, called dead ends. His colleagues left the field, funding dried up, students were told not to work with him. But Hinton never stopped believing that if we just had enough data, enough computing power, it would work. AlexNet proved he was right. After 40 years of being told no, vindication at last. After AlexNet, progress went from crawl to sprint. In 2013, nearly every ImageNet entry used deep learning. In 2014, VGGNet achieved strong results with 19 layers. Google LeNet used 22 layers with sophisticated architectural innovations. In 2015, Microsoft's ResNet achieved 3.6% error using 152 layers and a breakthrough technique called residual connections. Human performance on ImageNet is approximately 5% error. Machines had surpassed humans at visual recognition. The corporate response was immediate. In March 2013, Google's leadership realises they just watched the future happen and they're not part of it. They call Geoffrey Hinton. Price? $44 million. But here's what they're really buying. Hinton and his 2 graduate students who built AlexNet. The bidding war was so intense they closed the deal in weeks. In December 2013, Facebook established Facebook AI Research, aka FAIR, recruiting Yann LeCun as director. In 2014, Baidu opened a Silicon Valley AI laboratory, recruiting Andrew Ng from Stanford. In 2011, an AI PhD graduate could expect to earn an annual salary of $120,000. Good money, professor track money. By 2015, companies were offering $300,000 to $500,000 for fresh graduates. Top researchers? Well, compensation packages exceeding $1 million. For perspective, that's NFL player money for people who study math. The gold rush had begun. Deep learning spread rapidly beyond computer vision. Speech recognition error rates dropped from 25% to 5.5% by 2017. Machine translation. Google's neural machine translation, which launched in 2016, dramatically improved translation quality. Medical imaging. Deep learning systems began matching specialist pathologists in cancer detection. Scientific research. Applications in drug discovery, genomics, protein structure prediction. The revolution was comprehensive. It's March 2016. Seoul, South Korea. Lee Sedol, one of the greatest Go players in history, 18 World Championships, prepared to face AlphaGo. Go is vastly more complex than chess. After just 2 moves each, there are 130,000 possible positions. The total number of possible games exceeds 10 to the 761st power, more than atoms in the observable universe. As recently as 2012, AI experts predicted conquering Go was 20 to 30 years away, perhaps impossible. 200 million people watched the match. Lee Sedol predicted, "I will win 5-0, perhaps 4-1. In Game 2, Move 37, AlphaGo placed a stone in a position that seemed bizarre. The professional Go commentators, players with decades of experience, watch Move 37 appear on the board. That's a mistake. 10 seconds of silence. Wait, that's brilliant. I've never seen anything like this in my life. This is not human. Move 37 violated 2,500 years of accumulated Go wisdom. It looked wrong, but it was perfect. Final match score, AlphaGo 4, Lee Sedol 1. Sedol said afterwards, "I thought AlphaGo was based on probability calculation and that it was merely a machine. But when I saw this move, I changed my mind. Surely AlphaGo is creative." After his defeat, Lee Sedol did something remarkable. He studied AlphaGo's games. He learned from the machine. He studied, he got better. Go players everywhere did the same. The machine had become the gold standard and greatest teacher in the history of the game. Then 6 months later, DeepMind released something that made even AlphaGo obsolete. AlphaGo Zero. It learned Go from scratch, just the rules, no human games, playing against itself continuously. In 40 days it rediscovered thousands of years of human Go knowledge, then surpassed it. In December 2017, with AlphaZero, the same approach applied to chess and shogi. Chess mastered in 4 hours, shogi mastered in 2 hours, Go mastered in 8 hours. It then defeated the world's best programs in all 3 games. It's 2014. In a bar in Montreal, Canada, Ian Goodfellow, a PhD student, is celebrating with friends. They're debating how to teach neural networks to generate realistic images as current approaches aren't working. Goodfellow has an idea. He sketches it on a napkin and goes home to code it. By morning he has a working prototype. He had conceived an entirely new approach, generative adversarial networks, or GANs. The concept is elegant. Imagine 2 artists. One's a forger trying to paint fake masterpieces. The other's an art detective trying to spot the fakes. The forger gets better because the detective catches them. The detective gets better because the forger improves. They push each other towards perfection. That's a generative adversarial network. 2 AI systems competing, learning, improving together. In 2014 they produced blurry, barely recognisable faces. In 2015, recognisable faces, still obviously artificial. In 2016, increasingly realistic. 2017, highly convincing. Then in 2018, StyleGAN produced faces indistinguishable from photographs. The website "This person does not exist" demonstrated the capability. Every refresh showed a different face, photorealistic, detailed, convincing, of someone who never existed. This person, never born, never lived, generated by mathematics. GAN's found applications beyond faces: art generation, photo enhancement, style transfer, voice synthesis, and music composition. But they also enable deep fakes, convincing fake videos of real people saying things they never said. For the first time, AI raised immediate pressing societal concerns: misinformation at scale, erosion of truth, consent violations. The technology was advancing faster than society's ability to develop appropriate responses. Quick test: the trophy doesn't fit in the brown suitcase because it's too big. What is it? The trophy or the suitcase? You knew instantly: the trophy. But how? Your brain did something remarkable. It looked at every word, understood their relationships, weighed the context and figured out the meaning, all in a fraction of a second. Until 2017, AI couldn't do this. Language models read word by word, like reading through a tube. No peripheral vision, no seeing the whole sentence at once. In June 2017, 8 Google researchers published a paper with a deceptively simple title: "Attention is all you need." They created the Transformer, an AI that could pay attention to every word simultaneously, understanding context the way you just did. This enabled parallel processing, faster training, better long-range dependencies. Within months, Transformers dominated machine translation. Within 3 years, they powered virtually every major AI breakthrough. In October 2018, Google released BERT, bidirectional encoder representations from Transformers. BERT learned language by predicting missing words in sentences, understanding context from both directions. It achieved state-of-the-art results on 11 different natural language processing tasks. In June 2018, OpenAI releases GPT-1, 117 million parameters. Results? Interesting but limited, but they noticed something strange. As they made the model bigger, it didn't just get better, it got better in unpredictable ways. It was learning things they didn't explicitly teach it, so they tried something audacious. What if we made it 100 times bigger? In February 2019, GPT-2 was launched. It had 1.5 billion parameters. It could write coherent stories, summarise articles, answer questions, even write code. OpenAI's response: this might be too dangerous to release. The announcement sparked fierce debate. Should powerful AI be openly available or carefully controlled? No consensus emerged. In May 2020, they made it 100 times bigger again. GPT-3 had 175 billion parameters. Training cost $4 to $12 million. Data, 570 gigabytes of text. Basically a significant chunk of the written internet. And it could do something new: few-shot learning. Give GPT-3 just 3 examples of a task: translating English to French, writing product descriptions, coding in Python, and it could do that task. No retraining required. In July 2020, OpenAI granted limited beta access. Twitter exploded. Every day new demonstrations. GPT-3 just wrote my essay. GPT-3 just built my website. GPT-3 just explained quantum physics in the voice of a pirate. But the limitations were obvious too. Factual errors, logical inconsistencies, bias, sometimes pure nonsense. The question hung in the air: is this actually intelligent, or just really good pattern matching? No one had an answer, but everyone knew something fundamental had shifted. The period 2012 to 2020 was 8 years of AI evolution. In 2012, AI couldn't reliably identify a cat in a photograph. By 2020, it could write essays, generate photorealistic faces, beat world champions, and hold conversations. But here's what should terrify or thrill us, depending on your perspective. The progress from 2020 to today was even faster. By late 2020, the pieces were in place. Transformer architecture, check. Massive data sets, check. Unprecedented computing power, check. What was missing? That last piece of the jigsaw would arrive 2 years later. On November the 30th, 2022, OpenAI launches ChatGPT. 1 million users in 5 days, 100 million users in 60 days. Students used it to write essays. Programmers used it to write code. Writers used it to break blocks. And businesses used it to automate tasks. The New York Times called it the breakthrough of the year. Google, Microsoft, Meta, everyone scrambled to catch up. Governments started writing regulations. People argued about whether this was humanity's salvation or its greatest threat. Which brings us to today. Remember that phone unlock at the start of the video? That's why it works. Next time on the AI story, the ChatGPT moment that changed everything. The race to build multimodal AI. The regulatory scramble. And the question we're all living with, what happens when AI can do most of the things humans can do? If this story fascinates you, subscribe and hit the notification bell because the next chapter is happening right now. I'm Ian and this is the AI story. Thanks for watching.